Hi, today we're going to look at the force on a charge in a magnetic field. Our goals for this session are, we'll look at the force experienced by a charged particle in a magnetic field in a particular set of circumstances. We'll try to come up with a general equation for the magnitude of that force. And we'll go over what we call the right-hand rule, and that's what we use to figure out the direction of the force. Okay, so what we remember is that we have a relatively straightforward equation that tells us the force exerted on a charged particle in an electric field. And that is F, the force, is Q, this is the charge on the particle, multiplied by the electric field, F equals QE. So our goal today is to find the equivalent equation for the force exerted on a charge in a magnetic field. So we'll do some experiments and we'll try and figure out what such a force might depend on. Okay, and we'll do some comparisons between what happens with the electric field as well and what happens with the magnetic field. Okay, so in this case, we have just a charge in an electric field on the left side, and it's a positive charge, and when we let it go from rest, what happens is it accelerates down. And that's because there is an electric field that is directed down. So that's totally consistent with our F equals QE relationship. The charge feels a force down the same direction as the field because it's a positive charge. And so we have a uniform electric field here, so we have a constant acceleration. Okay, we'll try the same thing with a magnetic field. We'll let our charged particle go from rest in a magnetic field that's also directed down. Ready? Here we go. And absolutely nothing happens at all. Okay, so that's quite different when you compare the electric field case to the magnetic field case. The charge is stationary in an electric field, then it's only stationary for an instant because then you get a force acting on it that gives it an acceleration and makes it move. In the magnetic field case, the stationary charge doesn't even notice there's a magnetic field present. The magnetic field exerts no force at all on a stationary charge. Okay, so let's try something different. What we're going to do now is throw the charges into the fields and see what happens. Again, on the left, we simply have a uniform electric field directed down. On the right, we have a uniform magnetic field directed down. Both cases, the charge is positive. Okay, so we give the charge an initial velocity down in the electric field. And it just gets faster and faster and faster. The arrow attached to it is the velocity vector. So there's uniform constant acceleration. And so the velocity increases. If we try it in the magnetic field, again, this is the velocity parallel to the field, then it goes at constant velocity. Once again, the charge doesn't even notice there's a magnetic field present. The magnetic field has no influence whatsoever on that charge, and that has a velocity directed parallel to the field. Okay, so let's see what we've got so far. So our conclusions so far are magnetic fields exert no force on stationary charges, charges at rest, or on charges with velocities directed parallel to the field. You might even conclude so far that magnetic fields exert no forces whatsoever on charges, but we're about to find out that that's actually not true. You don't want to go that far. Okay, so once again, this is an electric field. So this is entirely an electric field. So this screen is just review. Okay? So now we have a uniform electric field directed down in each case, and we're going to throw a charge, either a positive charge on the left, or actually a neutral object, no charge, in the middle, or a negative charge on the right. We're going to throw these guys into the field. We're going to give them an initial velocity to the right, perpendicular to the field, and see what happens. Okay, so the field is directed down. And so we do this with a positive charge, and it feels a force in the direction of the field. And this is just like throwing a baseball, giving it an initial horizontal velocity near the surface of the Earth, and that will follow a parabolic trajectory, and that's what we see happen here. If we do it with a neutral object, then nothing happens at all, in the sense that the field has no influence on the neutral object, because the electric field acts on charges, and this thing's not charged. If we do it with a negative charge, then it feels a force going the opposite direction as the positive charge did, so it follows a parabolic trajectory that curves upward instead of downward. Okay, so that's the case of charges given an initial velocity perpendicular to the field in an electric field. Okay, so we'll try the same thing in a magnetic field. Remember, so far we haven't got the magnetic field to have any influence whatsoever on our charges. In this case, our magnetic fields are uniform but directed out of the screen straight toward you. Okay? So that's one difference between what we did with the electric field and what we did with the magnetic field. The electric field was directed down. The magnetic field in this case is directed out of the screen. Okay, so we'll try it with a positive charge. Positive charge, well, it looks like it starts off following the same trajectory that it did in the electric field, but then we clearly see it's not parabolic, it's circular, and that would keep going around and around and around in circles forever. And so actually what we get here is uniform circular motion. That charge just went around that circle at a constant speed. So that's cool. So now we finally get some influence between the magnetic field and the charge, some influence of the field on the charge. If we do it with a neutral object, not surprisingly, there's no effect at all. And if we do it with a negative charge, then it curves the other way. So once again, we get uniform circular motion, and we get the charge spinning around in a circle at a constant speed. Okay, so that's kind of a very interesting result. Okay, so let's just go over what we just saw. So just to summarize, magnetic fields, just like electric fields, exert no force on neutral particles. The force exerted on a positive charge is opposite to that exerted on a negative charge. That's also true for electric fields. And this is very different between magnetic fields and electric fields. With a magnetic field, the force on a charged particle is perpendicular to the particle's velocity and perpendicular to the field. And the movie here, animation here, shows a special case where the velocity and field start off perpendicular to one another. Okay, the velocity is the arrow pointing to the right, and the field is actually out of the screen, and the other arrow going down at the beginning is the force arrow. Okay, so the force is always directed toward the center of the circle, and this is completely consistent with uniform circular motion. Okay, now once again, we only get uniform circular motion if the velocity and field, magnetic field, start off perpendicular to each other. Okay, so now we'll try and figure out what the force depends on. Okay, so we'll do some experiments. So we'll do an experiment where we throw the positive charge into the field with some initial velocity, and we get a particular path. This is the same one we just saw on the previous screen. So we get a diameter of 5 units here, and if we double the field, then it turns out that we double the force, and our diameter is only 2.5 units. Okay, and both these charges would circulate forever and ever if we let them. Okay, but our conclusion here is that force is proportional to field. Bigger the field, bigger the force. Okay, so let's just go over that again. What we did observe was that the radius of the path was half as large when we doubled the field, and so our conclusion was doubling the field doubles the force, force proportional to magnetic field. Now that's quite similar to what we saw for electric field. There the force was proportional to the electric field too. By the way, the symbol we use for magnetic field is B. So when you see a capital B later on, that'll represent the strength of the magnetic field. Okay, now let's see if it depends on charge. Remember our electric force equation was F is QE, so the force there was proportional to the charge. Let's see what happens here. So we throw a charge Q into a field, we get a particular result. We throw a charge of 2Q into the field. Turns out there we get a force which is twice as large as what we got in the case where it was Q. We're keeping the velocity the same, by the way, the initial velocity. And then we do 3Q and we get 3 times the force with the 3Q case. Okay, so just like we got for the electric field, the force is going to end up being proportional to the magnetic field. Okay, so what did we observe? We observed the radius was going inversely with the charge, and again, that tells us the force is doubling when we double the charge, tripling when we triple the charge, and therefore we can conclude force is proportional to charge. Okay, so again, that's very similar to what we got with the electric field. F proportional to Q, both for electric fields and for magnetic fields. Okay, now this is something we did not get a difference for with the electric field case. In the electric field case, the force exerted by the electric field on the charge was independent of the velocity. The particle could be at rest, could be moving faster. The force was always the same, just QE, no V dependence. And as we see here, if we throw these particles into the field, first we do the particle with velocity v, then we do the particle with velocity 2v, then we do the particle with velocity 3v. Really neat thing about this, actually, by the way, is that all these particles take exactly the same amount of time to go around. They're all in the same field, they all have the same charge, but they have different v's. And what we see is that the force is actually proportional to the speed. So you double the force, that's the downward arrow you see there in the 2v case compared to the v case. You get triple the force in the 3v case compared to the v case. Now this is uniform circular motion, right? So if you look at the equation, r is mv squared over f, you might naively think that if you double the v, well, the v is in there as a square, so you would think that you might quadruple the radius. But you don't, you double the radius. Similarly, when you replace v by 3v and you square that, the 3v goes to a 9v squared. You might expect the radius in the 3v case to be 9 times as big as it is in the v case, but it is not. It is only 3 times as big. How do we explain this? So we observe the radius of the path to be proportional to the speed. That's not what this equation might naively expect us to believe. However, it makes sense if the force has a v in it. The force is proportional to the speed. Okay, then we get mv squared on the bottom. We get a v hidden inside the f. Mv squared is on the top. The v inside the f is on the bottom. And overall, we just get radius proportional to v. And that's what we observe when we do the experiments. And that's completely different from what we got with the electric field case. The electric field case, no v dependence. In the magnetic field case, F is proportional to V, the speed. Very interesting force behavior. Okay, so just summarize everything. No force applied on a stationary charge by a magnetic field or on a charge that is moving parallel to the magnetic field. If you reverse the sign of the charge, reverse the direction of the force. Okay, we've seen that before. The force is proportional to charge, Q, the field, B, and to the speed, which was V. And so we can write down an equation that says F is QVB, except it's a little bit more than that because we have to get the fact that when the velocity and field are parallel to each other, there's no force. Okay, so if you put a sine theta factor in here, where theta is the angle between the velocity vector, V, and the magnetic field B, If theta is 0 or 180 degrees, if V and B are in the same direction or in exact opposite directions, there's no force. You get maximum force where the angle is 90 degrees, and if the angle is 30 degrees or 70 degrees or whatever, you get somewhere between 0 and maximum. Okay, so the maximum value is QVB. That occurs where theta is 90 degrees. The minimum value is 0. And I'm just doing magnitudes here, so I guess really it's the, so sine theta I guess is sometimes negative, but let's not worry about that. Let's just take the magnitude of sine theta, and that's the magnitude of the force. Okay, now we're talking about force here, which of course is a vector. And so how do we get the vector out of this? Well, one thing to remember about the force is that it's always perpendicular to the velocity and always perpendicular to the field. So the vectors v and b define a plane. The force vector is perpendicular to that plane. Now that gives you two possible directions. Okay, for instance, if your plane is horizontal, then your force could be up or down. Okay, so the correct direction, you can distinguish between up or down with the right-hand rule. So we'll go over that. Another thing to keep in mind before we get to the right-hand rule is that a force is perpendicular to the velocity, and that's what this magnetic force is, cannot change the object's speed or the kinetic energy. All it can do is change the object's direction of motion. Okay? To make it go faster, you would have to have a force component in the direction of the velocity. We don't have that. To make it go slower, we'd have to have a force component opposite in direction to the velocity. We don't have that either. Our force is always perpendicular to the velocity, so it can't change the speed or the energy, kinetic energy. Okay, so here's a right-hand rule. Use your right hand, not surprisingly, not your left hand. You point your fingers on your right hand in the direction of the velocity. By the way, there are several ways to do the right-hand rule, several versions of it. If you've learned a different one and you're comfortable with it, feel free to stick with it. Okay, if you haven't learned one, or you weren't happy with the one you learned, here's the one that I'm going to use. Okay, fingers of your right hand in the direction of velocity. Then you want to curl your fingers into the direction of the magnetic field. Now, so your hand has to be oriented just right for you to be able to do that. So to figure out which way your hand should go, well, if V and B are perpendicular, it's relatively easy to do this. Point your fingers in the direction of V, the velocity. Point your palm in the direction of the magnetic field. Then your right hand is going to be held properly. Then you can curl your fingers into the direction of the field. You stick out your thumb. It should point perpendicular to the way your fingers were going originally and the way your fingers were going at the end when they were in the B direction. Your thumb points in the direction of the force if it's a positive charge. If the charge is negative, then your right hand lies to you, okay? In that case, the force is opposite to what your thumb says. So you look at your thumb, you say, okay, it's a negative charge, it goes the exact opposite direction, the force does. Okay, so let's go over that again with pictures. So here's a right hand. And in the picture on the left, we have a positive charge with a velocity initially directed up. There's a uniform magnetic field directed to the left. Okay, so in the right-hand picture, the fingers are curling from the velocity direction toward the magnetic field direction. Okay? And the thumb is sticking straight up out of the screen here. So again, point your fingers on your right hand in the direction of velocity, curl your fingers in the direction of the magnetic field. Your thumb points in the direction of the force experienced by a positive charge. If the charge is negative, the force goes the opposite direction. Okay, so that's how we get the direction of the force. And then we have this really neat equation, F is QVB sine theta, which has all these neat observations in it, right? If V is 0, no force. If V and B are parallel, no force. If V and B are perpendicular, then you get the maximum force you'll get in that particular, with those V and B combinations. So you get this neat force, a little more complicated than Q times E, QVB sine theta, but leads to some interesting results. Okay, so that's all for our little look at how charges act when they're influenced by magnetic fields, when they're in a magnetic field. Okay, so we'll carry on from there in class.